Hi everyone, Miss Lorette here. I'm going to walk you guys through section 5.1, which is rate of change in slope. I also created some printable notes that goes along with this lesson if you have access to that, as well as a way to print it. That's highly recommended to make taking notes a little bit easier. Otherwise, this is a video. Feel free to just pause it if you need a little more time to copy everything down if you're writing it in your notebook. Okay, so let's start by taking a look at this example here before we dive into the real meat and potatoes of this lesson. We've got these two individuals, Sam and David. They're pushing a barrel up a hill. For this particular example, let's also assume that they have the exact amount, same amount of strength, and that the barrels weigh the same. Who do you think is going to struggle the most and why? I encourage you to pause the video and think about it for a second. And hopefully you've given this question some thought. Don't you think that David is going to have an easier time than Sam? Why do you think that is? Most students would arrive to the same conclusion. They might have different ways of explaining it, but when you look at the hill that David is pushing his barrel up versus Sam's, it's not as steep, right? So that's why he's going to have an easier time. It doesn't have as steep of an incline. So in math, we have a way to measure steepness. We also have a special phrase that we refer to it as. It's called rate of change. Rate of change shows the relationship between two changing quantities. So as the name implies, if you recall from chapter 2, a rate is a ratio where we're comparing two different things. So let's go ahead and write down the formula for rate of change is. Your rate of change, I'm going to draw a big fraction bar here, because I'm going to write some stuff that's going to take up a little space in both the numerator and the denominator. Your rate of change is going to be the change in what's known as your dependent variable divided by the change in the independent variable. And hopefully you've learned these words in your science class. You've learned what a dependent versus an independent variable is. Okay, if not, we'll kind of go over it. But I encourage you to maybe look up this stuff, maybe even practice it a little bit on Khan Academy. I'm sure there's practice somewhere on there where you're identifying the difference between the two. But the short story of it is that the dependent variable is going to, as the name implies, depend on the value of the independent variable. Okay, the independent variable doesn't rely on anything. It's just going to change however it's going to change, regardless of the situation and how other variables are changing. And the way that we calculate change is we subtract. Oftentimes, I might abbreviate this giant formula as triangle dv for dependent variable divided by triangle IV for independent variable. This triangle means change. That's what the triangle means. It's actually a delta symbol in math. Okay, so hopefully you've got that formula written down. Again, if you don't know what an independent variable is versus a dependent variable, you should write this down as well. An independent variable, we often use x. Values don't depend on other variables. A common example is time. This isn't the only example of an independent variable, but it's a very common one. We can't change time. Time isn't going to be affected by any other variables. It's going to flow how it's going to flow. Okay, we would like to change time sometimes, but we can't. It's just going to flow the way that it's going to flow. A dependent variable, we often use y. The values will depend on other variables. So a common example might be the money you earn. For an hourly job, right? If you get paid hourly. An hourly job. So the money is going to be your dependent variable, and the hours you work, because that's time, that would be your your independent variable. So the dependent would be the money, your independent variable would be the number of hours you worked, okay? Because the amount of money that you earn is going to depend on how many hours you worked. And the hours that you work, well, the hours are going to flow however they're going to flow. You know, they're not going to go any slower or any faster, even if you'd like them to. So let's actually apply our rate of change formula and calculate the rate of change for a table of values. So this is one common example in which you may be asked to calculate the rate of change. It says the table shows the distance a band marches over time. Is the rate of change in distance with respect to time constant? Okay, so that's one of the questions that we're being asked. Is the rate of change constant? We're also asked, what does the rate of change represent? So it's important that you're reading the questions thoroughly and you're, answering all parts of the question. Here they're asking us to do not just one thing, but two things. We need to figure out, is the rate of change constant? Meaning, do we get the same rate of change every single time? Is it constantly going to give us the same answer? And lastly, what does the rate of change represent in the context of this problem? Let's go ahead and answer the first question. To do that, we need to determine which variable is independent and which variable is dependent, because I need to plug it into my formula, which is the change in the dependent variable divided by the change in the independent. And to calculate amount of change, I just subtract. So my two variables are time and distance. Well, I mentioned before, if you see time, that's independent regardless. So this immediately makes the distance my dependent variable. So I'm going to calculate the change in my distance and divide it by the change in the time. And I'm just going to use some consecutive rows here to make my life easier. Okay, so I can subtract these two distances, and it doesn't matter which distance I start with if I do 260 minus 520 versus 520 minus 260. It doesn't matter which order I do it, so long as I'm consistent with how I then subtract the time. So I'm just going to start with the bigger number because that's my preference, so I get a nice positive. So I'm going to do 520 minus 260. And because I've chosen to start with this second row here, I have to start with the same row in my denominator. I have to do 2 minus 1. So I'm going to do 2 minus 1. And now I'm going to subtract and get my amount of change. 520 minus 260, that's going to give me 260. 2 minus 1, that's going to give me 1. And this is fully reduced. I can't simplify that anymore because my denominator is already a 1. And understand that this numerator, it has a unit. This is feet. Remember, this is a rate. A rate is a comparison of two different units or two different quantities. My denominator is minutes. So just something to keep in mind. I'm going to do the same thing for the next row of values. So I'm going to do 2 and 520 and 3 is 780. So again, I'm just going to start with this bigger number here and then subtract the smaller. So I'm going to do 780 minus 520 divided by 3 minus 2. 780 minus 520, let's see, that's going to give me 260. And then 3 minus 2 is going to give me 1. So again, this is feet over minute. So far, it's turning out to be constant. I'm getting the same thing. That's what the word constant means. It's constantly the same answer. So I'm going to check the next row of values. And again, I'm just going to do the bigger number minus the smaller. That's my preference. Actually, maybe for this one, I'll show you if you go the other way, you'll get the same answer. So for this one, I'm going to start with the 780. 780 minus 1040. But if I do it this way, again, if I started with this row here, I have to start with the 3. So I'm going to do 3 minus 4. I'm just going to use a calculator to get through this calculation really quick. I don't want this video to be too long. That's going to give me a negative 260 in the numerator. And in my denominator, I'm going to get -1. So this can actually reduce a little bit. I can reduce the negatives and get a positive. So no matter what, I'm going to get the same rate of change. So because I'm getting the same rate of change every single time, that tells me that yes, the rate of change is constant. I've answered that part of the question, and then here's my work to justify my answer of yes. The next question that we're being asked is, what does the rate of change represent? Well, take a look at our reduced rates of changes here. This is 260 feet per minute. And remember, this is the distance that a marching band is marching over time. So if you think about it, this is their speed, right? This is telling me that they're marching at a speed of 260 feet per minute. I have no idea if that's fast or slow, but that's what it's telling us. The band, this is what I can write for what does the rate of change represent. The band marches, oops, let me fix that, make that a little neater, marches 260 feet per minute. And there's different ways to put this in words. You could also have said, per minute, singular. You could have also said that the band's speed is 260 feet per 1 minute. Every 1 minute, the band marches a distance of 260 feet. There's a lot of ways to write it in words, but you want to take this rate of change and include your units to kind of help you figure out how to put that into words and explain what the rate of change is representing. It's representing their speed, okay, or and how far they go every minute. All right, so here's one for you to try. We're going to use the same table of values. It says, in the previous problem, do you get the same rate of change if you use non-consecutive rows of the table? Explain. And again, there's different ways to justify your answer here. Non-consecutive means that you're going to use, for example, 260 and 780. Whoops, I didn't mean to jump to the next slide there. 260 and 780 or 260 and 1040. When I did it, I was using consecutive rows. I was going from 1 to 2, 2 to 3, and 3 to 4. Non-consecutive means you're not going to use rows that are one right after the other. So I'm going to pause the video. I'm going to work out a few examples. I encourage you to do the same, and then I'll unpause to give you some potential answers that students could have gotten. Okay, so here are some examples that I'm getting when I use some non-consecutive rows. Regardless of which ones you used and what order you did it in, you should have arrived to the same answer that the rate of change is still going to give you 260 feet over 1 minute. So it doesn't matter if you use non-consecutive rows, the rate of change here is constant, so you're going to get the exact same answer no matter what. So we should probably state our final answer. Do you get the same rate of change? Yes, you get the same answer. Same rate of change. And then here's my work to justify that answer. Okay, now in the previous section in 4.6, we did a little bit of graphing lines. We were graphing some linear functions. When you look at the rate of change for one of those lines, it will also be constant. In math, we actually have a word to refer to this type of rate of change when it's for a line. It's known as slope. We use the variable m to mean slope. And there's a few different ways to calculate your slope from a line. It depends on the information that you're given. I'm going to show you both formulas for each slope. So the easiest way to calculate slope, it's your rise divided by your run. Your rise is how much your y's are changing. Your run is how much your x's are changing. And again, your y's are your dependent variables and your x's are your independent variables. So you're still following that same rate of change formula. Rise is how much the line goes up and down. Run is how much the line is moving or changing left to right. And then you divide the two. So this particular formula is going to be very helpful when you're looking at a graph. You pick 2 points on that line and you count. How much do you rise to get to the next point? How much do you run to get to the next point? The next formula is more helpful when instead of looking at a graph, you're given 2 ordered pairs. You can also use this formula if you're looking at a graph as well. You would just need to state what the ordered pairs are. It's going to be y2 minus y1 divided by x2 minus x1. And these are for 2 ordered pairs, x1 comma y1 and x2 comma y2. So again, it's your change in your y, your change in your dependent variable, divided by your change in your independent variable. Now, some teachers might write y1 minus y2. Some teachers might not write those numbers at all and just write y minus y. It doesn't matter which of these 2 ordered pairs you label as the first versus the second. It doesn't matter which ordered pair you start with. What does matter is that in your numerator, you're subtracting the y values. In your denominator, you're subtracting the x values. And when you look at a given x and y that are stacked on top of each other, they come from the exact same ordered pair. Okay, so those 2 x's and y's come from this ordered pair, and this x and y comes from this ordered pair. That's the important thing. The order in which you begin does not matter, so long as you're keeping it consistent from that point forward. Okay, so let's do a little bit of examples where we calculate the slope, the rate of change for a line from a graph. So I'm going to do a few with you. I want the pen, there we go. So we've got a line here, and when we're choosing points to calculate slope from a line, you want to choose nice points that fall on what is known as a lattice point. A lattice point is when your line is crossing perfectly on these grid line crosshairs right in the center. Okay, so for example, this is a nice point right here because it's falling right in the center of these grid line crosshairs, right in the center. Here's another nice point because it's falling right on those grid line crosshairs. An example of a point that would not be good to use would be like a point right here, right? Even though those 2 points were already labeled and there wasn't a point labeled here, there actually is a point here. Remember, a line has an infinite number of points. That's why we connect it. We're showing that this line is really an infinite number of points that are all connected. So there's a point here, there's a point here, there's a point up here, there's a point right down here. These are all points. There's an infinite number because there's an infinite number of solutions. This point right here where my pen is hovering, that would not be a nice point to use to figure out what my rise and run is, because I'm going to have to estimate where it's sitting on that line. I don't know the exact value of my y here, and I don't know the exact value of my x. I can't just assume that it's right in the center. Maybe it's not in the center. Maybe it's not at 3.5 for the x value. Maybe it's 3.6. Maybe it's 3.678. Maybe it's 3.6 repeating. I have no idea. So unless it's labeled for me, I would have to estimate, and we don't want to do that. We want to calculate the exact value. So we don't want to use these values that sit in between these grid lines inside these grid line boxes. We want to use the nice lattice points where it falls right in the center of those grid line crosshairs, okay? So I'm going to use these 2 red points here, and I'm going to start by writing my formula. We use m for slope, and again, slope is rise over run. Now you might be wondering, which point do I start with? It doesn't matter. So long as you're calculating your rise and your run correctly, you're going to get the same slope no matter what. So I'll show you both ways. I'm going to start with this bottom point and go up to the top. I'll calculate my slope, and then I'll do it the other way, and we'll get the same answer. When I go from the bottom point to the top, I got to figure out how much do I rise first. So I rise however many times as it would take until I'm level with that next point. I rise 2 units. So that's going to be my numerator. And then I run to the right however many times it takes until I reach this next point. And that's going to be 3 units. Now, another thing that we need to take into consideration when we rise and we run is that our directions have signs. Up and right are both positive directions when we look at a graph. Okay, if that's not clear, look at how your axes are labeled. The upwards points on the axis are all positives for the y's. If we go down from the origin, those are negatives. So down would be negative. If we go to the right on the x-axis, those are all positive values. And if we go left from the origin, those are all negatives. So I get a positive 2/3 as my slope here. I'm going to show you using the other direction. And just so that way this is a little clear, I'm going to erase all of this so I can kind of start over. So I'm going to put my nice 2 lattice points back on there so they're nice and obvious, even though they've already drawn it. I'm going to start from the top point, and this time, instead of rising, I'm going to fall until I'm level with that bottommost point. So I'm still falling 2 units, but because I went down, that's a negative direction. And then from there, I'm going to run to the left 3 spaces, but again, because I went left, that's a negative direction. Negative divided by negative gives me a positive. I get the same slope no matter what. I'm going to do another example. I'll just do it one way here. They've already outlined some nice lattice points for us, so I'm just going to use those 2. My slope is rise over run. I'm going to go from this top point to the bottom. I'm going to rise 4 units, but I actually went down, so that's negative. And then I'm going to run 5 units. And since I went to the right, it stays a positive. So my final slope is a negative 4/5. And obviously, if you're getting a slope that can reduce to something smaller, you want to reduce it. And that's it. That's how you calculate slope from a graph. So I'm going to pause the video here. I'm going to give you a couple to try. And then when you unpause the video, you should see some solutions. Okay, so here are the slopes that I'm getting for each one. Regardless of which points you started with, you should have gotten a positive 2/5 for the first one and a negative 1/3 for the second one. Notice that it was 2/6 first and that it reduced. Okay, so let's calculate the slope for some ordered pairs. So instead of looking at a graph, we're given these 2 ordered pairs, -1, 0, and 3, -2. Again, we want to find the slope. It's best to start by writing your formula, which is going to be y2 minus y1 divided by x2 minus x1. And I highly suggest labeling your ordered pairs. So this is an x, this is a y, this is an x, this is a y. So we want to subtract our y values in the numerator. Again, it does not matter which ordered pair you start with. I could start with this first ordered pair if I want to and do 0 and then minus, and then a -2 is the second y value. So be careful when you're doing this. A very common mistake that students will often make is that they'll write minus, but then when the second number is negative, they forget to include that negative. You've got 2 minus signs here. One of them is a part of your formula, and the other one is the negative that's being input for that second value. So just make sure that you're including both. And then I'm going to divide this, and I'm going to subtract the x values. Now, the x values have to be from the same ordered pairs that I wrote down for the y values. In other words, what I'm trying to say is the order in which you write them has to be the same. So for the 0, I pulled from this first ordered pair right here. Well, for my denominator, I need to do the same thing. I have to start with that same exact ordered pair so that the x value and the y value that are, stacked one on top of each other like this, they come from the same ordered pair. And then I'm going to subtract the other x value, which is 3. So notice this -2 and this 3, these x and y values must come from the same ordered pair. And again, I'll show you flipped the other way, where if we started with this ordered pair, we would get the same answer no matter what. In my numerator, I can do keep, change, and change these double negatives to a plus. 0 plus 2 gives me 2. -1 minus 3 gives me -4. Their signs are the same, so I add and I match the negative sign. And this can reduce to a -1/2. So this is the slope that we should get. If I flipped these ordered pairs around and I started with -2 in my numerator, I would subtract 0, that's the other y value, and then for my x's, I'd have to go back to the same ordered pair. So I'd start with the x value of 3 and subtract a -1. So be careful. Again, this second value is a negative, so I want to write my minus sign first, and then my -1. -2 minus 0 is going to give me -2 in my numerator. These double negatives on the bottom make a plus, giving me 4. And again, this can reduce to -1/2. So it doesn't matter which way you do it, you get -1/2 as your final answer. Okay, so here's one for you to try. I'm going to pause the video, give it a go, and then when you unpause, you'll see the solution. Okay, so here is how I got my answer. You may have chosen to start with the other ordered pair. That's okay. We should still match in the end. So when I did it, I got a -4/3 as my slope. I decided to just start with this first ordered pair. Okay, so let's take a look at some special cases here. We've got a flat line here and a straight line here as well. This one's straight horizontally, this one is straight vertically. So let's go ahead and actually calculate our slope here. There's a couple different ways I can do this. We've got some ordered pairs that we've labeled here. So I could use the same formula I just used, or I could use the two ordered pairs that I see on my line. Again, it doesn't matter which 2 points I use. I could use these 2 points. This is also a nice lattice point. Here's a nice lattice point. It doesn't matter. I could do rise over run. I tend to use rise over run when I'm looking at a graph because that tends to be the easiest. So I'm going to do the same thing here. Now, when I look at this line, it's flat, left and right. Okay, so there's no steepness to it. It's not, rising from left to right, and it's not falling from left to right. So if I go from this point to, say, this point, I don't rise at all. I don't go up and I don't go down. So my rise here is just 0. But I can run, and it doesn't matter which point I do this with, right? If I go from this point to this point, I could I could run a +1, or I could run to +2. It doesn't matter what I do here. I'm going to get the same slope no matter what, because 0 divided by a number is just 0. Okay, so whenever you're looking at a horizontal line, your slope is going to be 0, no matter what. Slope is always 0 for a horizontal line. I often use the phrase for my students, if it's y, you fly, and we'll learn that later that these lines that are straight left and right like this, these are y equals without an x. So this equation would actually be y equals 2. There wouldn't be any x involved. So we'll kind of review that a little bit later. But for right now, just understand that when you're looking at a horizontal line like this, it has a slope of 0. You could have also used the same tactic and used these two ordered pairs and did, my y value minus my y value would be 2 minus 2. My x values, I could subtract those. 2 minus 2 in my numerator would give me 0. This would have given me -5, so I would have gotten 0 no matter what. Now let's take a look at this straight line that is straight vertically. I'm going to start by just using this point here, and I'm going to use the other point that they're labeling. So I'm going to go from this top point down to this bottom point. It doesn't matter which points you use. It doesn't matter which point you start with. I'm going to go down 3, so that's my rise, -3. But then to run to the other point, I was able to reach that point without running at all. I didn't move left or right. All I do is move up or down this line. So my run here is 0. Now, some students might say that this equals 0. It does not. Okay, if I divide a number by 0, and I encourage you to actually try it with a calculator and see what it says, it'll spit out an error at you. In mathematics, we cannot divide by 0. We say that this is undefined. That's why your calculator gives you an error. This is not equal to 0. So for a vertical line, a line that's straight vertically, m is undefined. It does not equal 0. These are two different slopes for two different lines. My suggestion, if it's not easy for you to memorize this and you tend to get them reversed, just do what I did. Pick 2 points, count rise over run, and then see what you get. If 0's up top, you'll get 0. If 0's on the bottom, you're going to get an undefined answer because your calculator is going to tell you it's an error. Oops. So the last thing that I'm going to wrap up this lesson with is just some little things to hopefully help you remember the different types of slopes. So this kind of goes along with what I was referring to in the previous slide, that if you get 0 up top, it's okay to have 0. If you looked at this O like a 0 in the numerator, this would just give you 0. No, it's not okay to have 0 on the bottom. This would give you an undefined slope. Okay, so hopefully this kind of helps you remember. Okay, 0 up top, it's okay. You'll get a number, you'll get 0. No, it's not okay to have that 0 on the bottom. You'll get undefined. And then I've just thrown a few things at the very end to kind of help you remember the different types of slope. If you imagine that someone is skiing up this line, the way that you would figure out if a slope is positive or negative, read it left to right like you would a book. If I read this line left to right, it would be rising, so that would be a positive slope. If it's falling left to right, it's going to be a negative slope. If it's a flat line horizontally, it's going to be 0. And if it's a flat line vertically, it's going to be undefined. And then last but not least, this is something I usually show my students, even though they don't really like it. I have some students that find it a little creepy, but it's a nice way to kind of remember your different types of slopes. This is Mr. Slope Guy. This line right here, as it's rising left to right, this is a positive slope. This would be my negative slope because it's falling left to right. This straight line vertically here makes it undefined. So this U stands for undefined. That's what's making his nose. And then his mouth is a horizontal line, which is 0. So his cheeks are the zeros. So hopefully all of this was very helpful to you. Feel free to rewatch anything if need be, and I will see you guys in the next video. Take care.